Welcome back to this course on polymer chemistry, and in today's 19th lecture I am going to cover the rest of the discussion on anionic chain polymerization, and then I will start our discussion on chain copolymerization. In this lecture we will try to cover anionic chain polymerization, which we started in the last lecture, and we will complete our discussion on termination reaction, and then touch upon the kinetics of anionic chain polymerization and also the molecular weight in this type of polymerization, and then talk about briefly about the practical aspects of anionic chain polymerization, and then we will start this chain copolymerization, which I will continue in the next lecture as well. Now, let us recap the lecture we had in the last time, lecture 18, where we talked about the cationic chain polymerization, kinetics and energetics, and we started our discussion on ionic chain polymerization, and we talked about general features of ionic chain polymerization and different types of propagation, initiation mechanisms, propagation, and we just started a few examples by which anionic chain polymerization can be terminated. Now, let us go back and just look at the initiation process once again in anionic polymerization. We had discussed mainly two types of initiator. One was organometallic compounds and another was electron transfer to reactant transfer reaction. Now, recollect from our discussion from last time that we had this given example of butyl lithium, which is a very strong electrophile. So, the monomers which does not propagate, the monomers which do not propagate with a very highly strongly stabilized anion, you require this strongly nucleophilic anion. So, this can be utilized to initiate anionic polymerization of say styrene, isoprene, and initiator like this, which are medium nucleophilic, they can be utilized to initiate monomers like methyl methacrylate, and this type of initiators, which are very weak nucleophiles, they can be utilized to initiate a very strongly or highly stabilized propagating anions like cyanoacrylate, because cyanoacrylate has two stabilizing groups. This has the propagating anion from cyanoacrylate is highly stabilized. So, you can actually anionically polymerize these cyanoacrylate monomers with a very weak nucleophiles. You can also polymerize with the strong nucleophiles as well, but this type of monomers can be polymerized anionically by very weak nucleophiles. Now, we talked about this electron transfer, the initiation by electron transfer example we gave is sodium and naphthalene, and we talked about propagation step and how propagation step depends on the solvent polarity, and we started our discussion on termination reaction for anionic polymerization. Now, if you can recollect from our discussion that it is in anionic polymerization you have no bimolecular termination, and in fact, in absence of any side reaction, if you have taken care of the condition reaction condition such a way that no impurity is present and you have taken care of all the other purity aspects, then most of this anionic polymerization actually propagate without termination. So, this anionic polymerization mainly happen without termination as long as termination as long you have inert atmosphere and extremely clean glassware and these things. Things like O2, CO2 they actually inhibit the anionic chain polymerization by forming peroxy or carboxyl anions which are very weak nucleophiles which cannot reinitiate a new anionic chain. So, these are inhibitors. So, extreme care should be taken to remove these O2 CO2 type impurities. Now, you can deliberately in most cases in laboratory we do terminate a propagating anion by adding some external reagent. For example, if we add in a polystyrene anion we can add water and this chain gets terminated and you get OH minus, which is this is very weakly nucleophile. So, it cannot further initiate a anionic chain. So, reaction actually gets terminated in these steps. Now, utilizing this concept you can actually synthesize functionalized polymers which are also called telecalic polymers which we discussed in the last class. For example, if we terminate say I write a general expression of a general polymer and you terminate by carbon dioxide and then acidify the reaction medium, you get carboxylic acid. You do the same thing say with a ethylene oxide and then acidify, you get a alcohol. Now, you can even functionalize this by such reagent and here you can make a polymer with a functional group at the end. So, it can be utilized this polymer which is also known as macromonomer because it can act like a monomer and start polymerization once more time. So, it is basically macromolecules with a behaving like a monomer. So, we often call this thing as a macromonomer. So, you can create in this way macromonomer also which you can utilize for further polymerization. Now, you can synthesize telecalic polymers by taking a initiator which is already functional groups. For example, if I take a trimethylsilyl protected imine Now, you can initiate a polymer chain and at the end you can terminate the chain, and then by acid hydrolysis you can make a amine terminated polymer. So, using these termination reactions with a definite reagents, you can actually create, you can terminate and as well you can create functional groups at the end of the polymer chain. So, which is very useful and which can be utilized for several other applications. You can take help of coupling reaction and you can make four-arm, in this case a 4-arm star polymer. So, these are the examples by which these are examples from how you can utilize ionic polymers and can make functionalize and the polymers of having different geometry. You can make, as we have discussed several times in last lecture, that you can utilize this end, and if you add a next second monomer, you can actually make block copolymer as well. So, if you take this type of chain and you can add second monomer B, then you can make a block copolymer. Now, in anionic polymerization, this lot of side reaction can happen by which the polymer chain can get terminated, and it is especially valid for polar monomers. For example, if I take a acrylate and let us consider a propagating chain, and it can actually abstract a hydrogen, and this chain can get terminated. And you can form this, can now reinitiate the polymers by which it can form branches. So, this one chain can get terminated by this side reaction, and you can form a branch in another growing chain. Now, that is not applicable for monomers like methacrylate, where this hydrogen is absent, but methacrylates actually can participate in several side reactions. For example, if I write this, say let us say example of methyl methacrylate. Okay, this is the chain end where you have a carbon ion. Now, it can actually form a cycle and it can knock out this methoxy and terminate this chain. So, I can write now this is a dead chain. So, the chain get terminated and this is a weak nucleophile as we discussed earlier. So, it actually often cannot reinitiate an ionic polymerization, and even it does, it actually slowed down the reaction a significant way. Now, another side reaction which is very possible, very prominent in case of methyl methacrylate is as follows. It is actually a reaction on the monomer, not on the polymer. This is a reaction monomer with the initiator molecule itself. Now, it can do a substitution reaction here, substitution nucleophilic reaction here, and form again a methoxy group here. Now, this is a different monomer altogether compared to the original methyl methacrylate monomer. So, basically now if the polymer starts, is actually a copolymer of methyl methacrylate and this monomer, and also not only it makes a copolymer, the reaction also gets significantly slowed down again because of the weak nucleophilicity of this generated anion. Now, if the reaction is slowed down, then the dispersivity problem comes, the polymer becomes much broader and the leavingness becomes difficult to maintain. So, there are strategies which are utilized to minimize this side reaction, especially for the polar monomers. So, we discussed for examples like for methacrylates. Now, if to slow down this reaction, one strategy is used very often is to take a bulky anion initiator. So, that sterically this reaction, these substitution reactions become problematic. So, this reaction, this side reaction becomes difficult. For example, instead of taking butyl lithium, this is a say taking butyl lithium, if you take a bulky lithium group like 1 diphenyl hexyl lithium or say cumyl lithium. Now, in this case, because these groups, this R group in this case are very large in size, this reaction, this side reaction of substitution nucleophilic reactions becomes slowed down, difficult. So, you can actually suppress this side reaction. If you think about the side reaction, that intramolecular cyclization reaction we just discussed here. And now, fortunately, the activation energy for this reaction, is higher compared to the normal propagation reaction. So, you can take advantage of that difference in activation energy and you can decrease the temperature. Now, if you decrease the temperature, both the normal propagation and this intramolecular cyclization slowed down, decreases, but because the activation energy for this cyclization reaction is higher. So, the drop in rate of this cyclization reaction is much higher compared to the normal propagation reaction. So, in that way you can actually minimize this side reaction. Another way to minimize this sort of side reaction is to use little polar solvents like THF. In that case you get solvent separated anions, initiator molecules. So, you can actually combine these three strategies like using polar solvents like THF and do reaction is at much lower temperature, say like at -78 degree centigrade, and use bulky initiator. So, by using these three strategies you can actually minimize this side reaction for methyl methacrylate and carry out adjacent anionic polymerization for methyl methacrylate, and this similar sort of strategy can be applied for other polar monomers as well. Now, as we have been talking that this anionic polymerization proceeds without termination, but that does not means that these anionic chain ends live forever. There are some intrinsic self termination steps possible, which are actually very slow and extremely slow. So, in normal time frame you can call those reactions are absent, but during a longer time frame those reaction could be significant, and then by that process that termination the chain could be get terminated. For example, if we take this electron transfer initiation reaction of styrene, now you have seen now you can undergo a hydride elimination and form a allylic end. Now, this actually can, this is a very acidic proton. So, it can be easily abstracted by a anion which could be another chain end, the styryl chain end. So, this proton can be abstracted by another propagating chain end and form now this is unreactive molecule. So, this is one example by which that polystyryl anion is self terminating and finally ending into a unreactive or terminated polymer chain. But these reactions are very slow, as you can see that hydride elimination is always slow, and if you compare with a cationic polymerization we talked about, in that case it was actually a proton elimination which was much comparatively much easier to things to happen. So, in comparison to a cationic polymerization and anionic polymerization, anionic chain ends are much more stable compared to a cationic chain end. So, in anionic chain polymerization you actually consider that this polymerization happen without any practical termination steps. Now, let us talk about this kinetics of anionic polymerization. Now, before we go into detail, let us recap what we learned in anionic polymerization, so that our kinetics understanding will become easier. Now, we know that in case of anionic polymerization, the initiation is faster. Now, remember the discussion we had for radical polymerization, radical chain polymerization, where the initiation steps is much slower compared to propagation step. But in this case, this ionic polymerization, the initiation steps are much faster compared to a propagation step. So, each initiator generates, and also each initiator, if you taking about the organometallic butyl lithium or a say sodium and naphthalene electron transfer reaction, each initiator molecules actually generates a single carbanionic center, active center. So, basically number of moles of initiator is basically will produce same number of moles of polymers at the end of the reaction. The chains are initiated at once because the initiation steps are much faster. All the chains are initiated, at a go. So, this all starts together, and all the initiators actually get consumed before propagation reaction actually starts. And as you can now visualize that all the chains now, after the initiation is complete, all the chains will grow simultaneously under identical condition, and unless we have any impurities or we want to stop or terminate the reaction by adding some agent, there is no termination reaction. Actually, there is no or very little depolymerization reaction depending on the sealing temperature of the polymer as well. So, we can write that K I is much higher than K P, rate constant for the polymerization, and rate of polymerization, which is again the standard way of writing K P, and again it is a, as we can remember the discussion for radical polymerization, you can write it is a bimolecular reaction between a monomer and a carbanionic chain end. So, you can write monomer concentration and the concentration of all the anionic species present in the reaction medium. Now, what is A minus? The concentration of all the anionic species present in the reaction, it is same as the initiator concentration, because as we discussed that each initiator actually initiates one chain. So, the concentration of the anions would be same as the concentration of the initiator molecules. Now, this expression is satisfactory for homogeneous and reactions in polar medium. In non-polar medium, what happens, there is a possibility that the initiator molecules can aggregate. For example, if you take a butyl lithium in non-polar medium, it can actually aggregate, and that depends on which butyl group you are taking. A number will vary from 4 to 6 or something. So, what is to remember that if we take a very non-polar medium or hydrocarbon medium, then this initiator molecules can actually aggregate, effectively reducing the concentration of the available initiator, which means this you have to compensate or you have to take care of that correction in the concentration of initiator terms to actually get the rate of polymerization. And as you can visualize or you can explain that because there is no termination reaction and the generation of initiator or the initiation is much faster, the concentration of these anionic species are much higher than a radical polymerization. For example, concentration of anionic species is almost like 10 to the power 5 times higher than m dot in a radical chain polymerization, which makes R p for anionic is much higher than R p for radical, and that is why these anionic reactions get over in very short time, and even in few seconds. Sometimes reaction is so fast that in a fraction of seconds this polymerization is completed. Now, what is the effect of solvent? We have discussed earlier that the solvent plays a very important role in terms of rate of polymerization of this anionic polymerization, especially in case of anionic polymerization. Now, let us we know that at different state of aggregation, we have discussed earlier that these ion pairs present in different state of aggregation forms a tight ion pair to solvent separated ion pair to completely free ion pair. They could exist depending upon the polarity of the medium, they can exist in different state of aggregation, and that state of aggregation will definitely determine the reactivity of the anionic groups at the chain end. If this is the ion pairs are totally separated, they are free ion pairs, obviously the reactivity of the ions and anions are higher. So, the R p would be higher compared to if the ion pairs are in contact or if they are tight. In case of, if you have consider same solvent, same say nonpolar solvent, the cationic, in case of cationic polymerization, the ions are not as tight as in case of anionic polymerization, because the size of the counter ions like lithium in beta lithium case or some, they are small. So, the anions and the cation in case of anionic polymerization are much more tight. So, for a given solvent, especially in non-polar solvent, the rate of cationic polymerization is higher compared to anionic polymerization, is about 2 to 3 times higher. And because in case of anionic polymerization, they are in non-polar medium, they are tight. So, effect of solvent polarity, if you increase the polarity for both case cationic and anionic, the effect in case of anionic polymerization is much higher, because to begin with they are much tight, and if you increase the polarity they can be free. So, the reactivity goes up. And if we talk about the effect of counter ion, so let us consider first the polar solvent. If you consider polar solvent, that means the ions are either solvent separated or they are free anion, and in that case the solvation, the separation, ion separation is more feasible for a small ion like lithium, a small cation for lithium, because lithium will be much more solvated in a polar solvent compared to a larger size ion cation like cesium cation or a potassium cation. So, if you are talking about a polar solvent, then small counter ion, counter cation will help in separating those ion pair, and hence the reaction rate would go up. Now, in the case of nonpolar solvent, where the ions, the anion, carbon ion and the counter ion are tight, then its, if it is the size is higher, the ions are little loose. So, the reaction is higher. So, in case of polar solvent, for a given anion, lithium cation will have a higher reactivity than sodium and potassium and cesium, and a non-polar medium it would be, order would be the reverse. Now, what is the temperature of the reaction in case of anionic polymers? It is little complicated, and it is not very generic way you can actually explain the effect of temperature in case of anionic polymerization. It depends upon the ion pair and the solvent, the polarity of the solvent. But to say least that in polar solvent you have what happens if you increase the polarity of the solvent, the contact ion pairs gets separated, and this process, by this process the individual ions get solvated, and as a result it is exothermic process. Now, it is a exothermic process. So, if you increase the temperature, the ions would be preferred to left hand side, which means the ions will be moved towards a tight ion pair sides, comparatively. So, if you compare between, let me write down these things. So, in a polar solvent, you have say contact and as I said, all these ion pair aggregation are in equilibrium. There always a very fast equilibrium exists between these two. So, a solvent separated ion pair. As you know, this would have higher reactivity and higher reaction rate compared to this, and this have exothermic reaction. So, if you increase the temperature, what happen, this goes to left hand side. So, by increase the proportion of contact ion pair in this equilibrium, and by that it decreases the rate of the reaction. In nonpolar solvent, basically there is no solvation. So, del H is 0. So, basically the temperature has minimal effect in terms of reaction rate. But sometimes what happen in case of nonpolar solvent, this aggregation of the initiator molecules, for example, like butyl lithium, we just talked about that in nonpolar medium butyl lithium could be existing in a aggregated form. Now, that aggregation could be affected by temperature, and it is actually lower temperature, the aggregation is less. So, as a result, if you decrease the temperature, the aggregation become less. So, the reaction become faster. So, the reaction rate goes up. So, in both cases actually decreasing the temperature actually might give you a better or higher reaction rate. So, we have now discussed the kinetics, the rate of reaction in case of anionic polymerization, and let us talk about the molecular weight of the resulting polymers in anionic polymerization. Now, we know for a chain polymerization how we define the molecular weight, how we calculate is the moles of monomers consumed divided by the moles of polymer chains produced. The moles of monomer chains monomer consumed will given by the conversion multiplied the initial concentration of the monomer, whereas the moles of polymer chains is nothing but the moles of initiator molecules present at the beginning. Now, we will have to add a factor k, where k is 1 for case of initiation, where each initiator molecules forming one chain, like butyl lithium case, organometallic case, where each initiator molecules are actually forming one chain. Now, in case of electron transfer initiation, 2, remember the sodium naphthalene case, actually 2 initiator molecules are forming one chain. So, you have to multiply the factor 2 for that. So, for normal in most cases K is 1, and there are cases like the initiation by electron transfer reaction where you have biradical, a chain grows from both the sides. So, basically the number of chains actually become half, effectively become half. So, the molecular weight becomes twice. So, K is 2 for initiation by electron transfer initiation. Now, if you have a monomers which for sealing temperature like alpha methyl styrene which are very few, where whose sealing temperature is very low, then you cannot just use this as such, then you have to consider the depolymerization reaction as well. But in most of the cases this sealing temperature is quite high compared to our reaction temperatures. So, those depolymerization reactions do not contribute at all. So, we do not have to worry about the backward reaction. So, we can use this expression to determine the number average degrees of polymerization in anionic polymerization. Now, what about the polydispersity MW by Mn? Now, this remains very narrow, say less than 1.05, something like that. It remains very narrow as long as your initiation rate is much faster compared to propagation. So, all the chains actually start, as long as we maintain this happens, then all the chains start from same time and proceed or propagate for same time. So, the polydispersity becomes very narrow, and so as long as you maintain or the reaction have initiation reaction is faster compared to propagation reaction, and also in there is no termination reaction. If you have termination reaction, then number of chains would increase than the expected one, and as a result your polydispersity would go up. So, as long as you maintain a pure environment where you reduce or minimize or make no termination reaction and your initiation rate is much faster compared to propagation step, then you can actually get assured that the polydispersity in anionic polymerization would be very narrow, so less than 1.05. So, let us now compare a few practical consideration. Now, we know that we actually know all these things, but just to conclude this anionic polymerization part, what are in practice what we need to do, as we have seen that the anionic polymerization is very susceptible to the impurities presence like oxygen, carbon dioxide, water, or if there is moisture present, it immediately will kill the anion, carbon anion. So, you have to be very careful not having any presence of these impurities. All the reagents which are using monomers and the initiator must be extremely pure. There should not be any other impurities, because the anionic carbon anions are very reactive. So, they can actually react with those impurities and get terminated. Now, to create a inert atmosphere, we typically use nitrogen and argon in the lab. So, the nitrogen and the argon you are using in the lab to create an inert atmosphere, that has to be extremely dry without moisture and extremely pure, and that is a really challenging job for the scientists who actually practice this anionic polymerization. There are several columns through which they send these gases before they actually can utilize these gases to create the inert atmosphere in the reaction environment. And your glasswares has to be clean. In practice, they actually the scientists who actually carry out an anionic polymerization reaction, they actually flame dry, which means they actually heat the glass wires under flame and then apply vacuum continuously. So, any oxygen, any moisture which was absorbed or any impurities which was there in the surface of the glass wire, they get cleaned up. So, as you can now recognize that it is not a very simple reaction to carry out in a large scale, in industrial scales, where maintaining all this purity, all these reaction conditions are very difficult, and as also these reactions are typically done at sub-ambient temperature. So, maintaining in a large scale industrial setup is quite difficult. So, as we expect that commercial applications of anionic chain polymerizations are limited, and they are not used for making many polymers, and they are only utilized for making specialty copolymers and some molecular standards where you would require a very narrow dispersion, which you can utilize for using standards as a molecular standards, which you can use for molecular determination. So, then the end of this module of chain polymerization, let us conclude with just a few basic comparison between the radical and anionic chain polymerization we studied. And we know that anionic polymerizations are very susceptible to impurities, whereas radical chain polymerization are also sensitive or susceptible, but not to that extent of this ionic polymerization. You can actually afford to have some degree of these impurities in case of radical chain polymerization, and that is why this radical chain polymerization are utilized in industry in a large setup much more frequently than ionic chain polymerization. And ionic chain polymerization are very sensitive to solvent polarity, as we discussed for last 2 lectures, and especially for anionic polymerization. Radical polymerization are not sensitive in general, but there are some polar monomers which can be sensitive to solvent polarity, but in general radical as long as the monomers are soluble in the solvent you are using, your reaction should proceed well. Ionic reactions are generally carried out ambient or lower temperature, as we have discussed. The activation energy for radical reactions are much higher compared to the ionic group polymerization, which are very low and sometimes negative. So, as a result, radical polymerization are done at comparatively higher temperature and typically higher than 50 degree centigrade in the lab and the industry, and this is obvious that radical scavengers stops radical or inhibit radical polymerization, whereas it has no effect on ionic polymerization. And this is why you take trouble of all these reaction conditions for ionic polymerization. These ionic polymerizations can be easily employed to tailor made copolymers like block copolymers, graph copolymers, which have a very niche applications where you do not need in a larger quantity, but in small, if you require a small amount, then you can utilize this anionic polymerization or cationic polymerization, especially anionic polymers, which are very useful to making block copolymer. Okay, with this we come to the end of this module on chain polymerization. What we now start is chain copolymerization. So, let us start our discussion on chain copolymerization. Now, remember when you talk about step polymers, we gave example how we can make step copolymerization if we have say 2 different acids, diacids. You can react with a diol and make a polyester. In that case, it is a copolyester because it has both R dash and it actually consists of 2 monomers, 2 different diacids. Now, as you can anticipate or you can realize that in case of step copolymers, the final copolymer should have same monomer, same ratio of the monomers as in the feed, because as we know that to make a high molecular polymer in case of step polymerization, the conversion has to be close to 100%, and if its conversion is 100%, all the monomers actually are in polymer. So, what is the feed ratio of the different monomers has to be same as in the polymers as well, copolymer as well. And we also know that chain step polymers actually is equilibrium polymerization, where the reaction is slow and different shapes are different sizes of oligomers or polymer are in equilibrium. So, at the end you invariably land up in a random copolymer, random arrangement of these two monomers, two monomers, unless specific cases where the reaction rates are very high, for example, reaction between acid chloride and alcohol, and if you take out that if you take out the resulting polymer from the solution, then there is a possibility that you can get the arrangement of these two monomers other than random, for example, block nature. But in normal cases, in normal case step polymers always gives you random copolymer. What happens in case of chain copolymerization? So, if you start with two monomers M1 M2, you can have M3, then typically we write tar polymer, and there are mostly three types of arrangement. So, if you consider M1 and M2, there is three types of copolymers you can have, which I think I have discussed in the first lecture in the introduction. One, this M1 and M2, the two monomers can get into the copolymer chain statistically following a statistical law, and one of the laws could be the Bernoullian statistics, which is basically nothing but the random arrangement of these molecules without any bias. So, like there is no bias on the incorporation of the two monomers one after one. So, there could be other statistical law which the monomers can follow, but this is one example which actually gives a complete random arrangement of these two monomers. So, this is statistical copolymer, and this particular case of which is lot of time people make these two as equivalent, but they are not in true sense, they are not equivalent. Random copolymers are not always statistical copolymers, but of course, statistical copolymers are random copolymers. Only the statistical copolymers which follow this law, they are called random copolymers, which are very common anyway. Most of the statistical copolymers are random copolymers, but not always. The second type is alternate copolymer, where you have alternate arrangement of these two monomer, and third is block copolymer, where you have a significant longer chain of say M1 and a significantly longer chain of NTP. That could be repetition of this one polymer chain could have several blocks, but this length should be significantly higher. So, that we can call them block. Now, block copolymers also could be different types like linear, the type we just showed, it could be graft block copolymer, where you basically have one chain A all from M 1 and with side chain of M 2. It could have brass arrangement, where basically we project it to 2 dimensional, where you have a surface of A and the brushes are hanging of the other monomers. So, you can basically extend this graft polymer into another dimension to get brass copolymer. So, these are all basically block copolymers which have a long sequence of 2 different monomers. Now, why do you need copolymer? What is the utility importance? Now, with the homopolymer, we all example we talked about polystyrene, polymethyl methacrylate, polyvinyl acetate and all these things. Actually, you can, the options are very few. In true sense, you can have only a set of homopolymers, not much. You can actually name a lot of homopolymers, but they are all the homopolymers. So, your options are limited with homopolymers. If you make copolymers, if you take M 1 and M 2, then you can choose from that monomer set and get several combination of M 2, M 1 and M 2, and not only that, for a given set of 2 monomers you can make different composition 0 100 10 90 to 90 10 and different composition. So, not only you have choices of choosing 2 different monomers from a set of monomers, also you have a choice of making different composition of this copolymer as well. So, basically there is an unlimited number of polymers you can copolymers you can make, or polymers you can make by using copolymer. Now, you can argue that you can mix these homopolymers or make a blend. You can always argue that okay, I have all those homopolymers, now I can mix them in different proportions to get the composition of what I want, which will finally give the same composition which you might get in the copolymers. But what happens if you start with 2 different homopolymers and mix them, a lot of time they do not mix. We will talk about maybe in later part of this course that polymers usually high molecular polymers, they do not exactly mix well. So, what happen, you require a combination of homopolymers or combination of monomers. So, to get a average or to the improved properties. So, what we will do, we will start from this importance part in the next lecture, and we will talk about details of chain copolymerization in the next lecture.